Hello, I'm Morgan Arona, and I will be introducing this product on a portable gravity-fed modular water filtration system, and I'll be introducing the need statement and the market analysis. So the first question is, who actually needs a filtration system and why? Right now, more than 2 billion people don't have access to reliable, safe drinking water, and during major disasters like hurricanes, earthquakes, or flooding, even developed regions can lose access to clean waters for days or weeks. Relief organizations like the Red Cross and UNICEF step in, but one of the biggest challenges they report is the lack of affordable, scalable water purification systems they can distribute quickly. Most existing portable water filtration systems on the market are designed for hikers' individual use. They usually cost anywhere from $30 to over $100. That might be fine for camping, but it's totally unrealistic when an organization needs to buy tens of thousands of units for emergency zones or refugee camps. Many of these products also require pumping or pressurizing, which adds complexity in the field. So our need statement is pretty straightforward. There is a real need for a low-cost, electricity-free, rapidly deployable water filtration system that can be mass distributed in disaster zones and rural low infrastructure communities. Moving into the market analysis, our primary customers are large humanitarian groups like the Red Cross, UNICEF, WaterAid, and FEMA, along with refugee camps and off-grid communities that need a reliable source of clean water. These groups aren't just buying a few units, they're buying in bulk, and cost is the number one constraint. There's also a secondary market in outdoor recreation and emergency preparedness, but our design is intentionally optimized for humanitarian deployment first. But when we are comparing existing products like LifeStraw or Sawyer, they're solid filters, but they aren't modular and their cost significantly more, usually $30 an up. Our system at around $10 is dramatically more affordable, which makes it a viable option for bulk NGO procurement. And because it's a gravity-fed and modular, it's easier to scale, easier to maintain, and better suited for the variety of water quality conditions these groups face. So in short, there's a huge global need, a clear market, and a gap that current products don't fill. Our design directly targets that gap. Thank you.
Why our product? Why our customers might prefer our product over its competitors is that it's simple to use. It's lower cost than other competing products due to low manufacturing costs and its simple assembly. And it's more durable and easier to maintain than other competing products because of these reasons.
Okay, so concept of operations. For our first concept, the modular slow sand filter, we pour water on the top, then gravity runs its course, pulling the water through the sand. Then a user would have to collect the clean water, skim out any of the sand fragments, and we expect this to last about 10 years or so with regular cleaning. On the contrary, we have the second concept, which is a pump integrated system. This can be a charcoal, this could be a micron filter. It is a filtration device with a pump that is pressurized. It does not use any electricity whatsoever. It's completely mechanical, simple enough. You just connect a hose. The pump draws through the water through the filters. It has a very fast output. Of course, you'll still have to rinse out the filter and replace cartridges as needed. And then for our third concept, we have a backpack filter. And for that, it's just a wearable backpack where we use a straw that we would suck on that will pull the water through a filter. And this is meant to be a more mobile unit. And with that, for the concept of operations for this one, you just take it as is. You have to fill the thing, you suck through the hose, and then of course you'll have to backflush and drain to reuse. And additionally, for our system requirements for the first one, we expect 1 to 2 liters per hour for the use of gravity. We need a minimum of 15 kilograms just for it to have the maximum capacity of flow rate. For durability, we need at least a 1 meter drop with no cracks or leaks just to show that it's durable because it is going to be holding sand and water. For the lifetime, we want it to maintain 80% flow rate after 2 years. And for maintenance, all you have to do is clean the sand at the top layer. It should only take about 5 minutes of time to do and hopefully result in about 90% for flow rate. For the second concept, that integrated system, we need it to operate at 1.5 bar and be able to withstand 3 bar. For the flow rate, we want anywhere from 5 to 19 liters per minute, so heavily faster, but it requires continuous pumping. Of course, the pump is a manual pump. It's going to require about 60 newtons of force. We want it to remove at minimum 99% of bacteria. And for durability, it's going to be the hosing and anything else really connected to it. It needs to withstand about 10,000 vibration cycles is the goal, what we hope for. For the third concept, that backpack filter, it's going to have drinking pressure. So that's how you suck on it. And that'll be about 0.2 bar. The hose itself needs, or the thing, the straw that you suck on needs to have about 100 newtons of tensile stress It needs to be able to handle that because it's going to be going through a lot of wear and tear since it is a mobile unit. Along with that, for the lifetime, it needs to be able to withstand 10,000 drinking cycles without leakage. And once again, that adds to that wear and tear. Lastly, we have the 0.5 liters per minute for the flow rate. Now, for project management, looking at this is the general idea of how we expect production to go. We have our concept and research where we go through market research, user needs, filtration goals, and feasibility. Is it even worth doing? And you can see right at the top there, we have the 1 to 2 section. So this is weeks, right? And so we expect the first 2 weeks to really figure out what we're trying to go for. Even if we do this whole proposal, we still need to research it heavily to make sure we have a sound product. Then for design and prototyping, we go through the concept design, material and filter selection, any type of 3D modeling like CAD or SolidWorks, and prototype fabrication/testing. And that goes hand in hand with testing and validation, which we expect them to coincide. Of course, validation and testing will go past, but there'll be some changing, some restarts, some bugs in the process. We expect that to happen. And so we have testing and validation with lab testing, flow and pressure, durability test, the compliance check, and of course, user feedback. We want to know if people will actually be interested in this. Then for the manufacturing, and the process and production and launch, we have processing design, budget, production, scheduling, and of course the pilot run, inspection, packaging, marketing, and full-scale production. And all that goes hand in hand until production fully takes off.
My name is Emily Lopez and I'm gonna be sharing about financials. To raise our required amount of money needed, we are pursuing 4 funding sources. First, government grants. Second, potential partnerships. Third, non-governmental and non-profit organizations. And fourth, investment through locals or teams contributions or loans. The plan is for a 2-year deployment in which the total amount of capital required is $643,200, and as shown in table 20, we can see the category and the amount of money required to fund the company. The investment timeline consists of 5 phases, each lasting 3 to 5 months. This outlines the required funding and purpose for each phase. Our filtration system costs approximately $6.35 to produce per unit. We offer a wholesale price of $9.99 for NGOs and government partners to ensure it remains affordable. For commercial consumer, the retail price is set at $13.99, while we use an average planning price of $12.15 per unit. This pricing structure enables us to cover our costs and generate sustainable revenue. Our total project cost is $643,200, and with more than 100,000 units sold, our total revenue reaches $1.3 million. This gives us a cost-benefit ratio of about 0.5, meaning we spend 50 cents for every dollar of benefit. This indicates the project is financially efficient and sustainable. Our startup investment and our total return reach give us a gross profit of $655,400 and a net profit of $12,200 after expenses. Using our return on initial investment, our return on investment is calculated to be 202%, meaning the project generates more than double the value of the initial investment.
Hello everyone, I'm Dev. Today I will be presenting the financial and production plan for our water filtration system. To start, we look at personnel cost, which includes both production and support roles. Hourly wages are between the range of $21 per hour to $29.5 per hour. These rates align with industry standards, helping us maintain efficiency while offering fair compensation. Direct personnel cost for year 1 is calculated based on 40 hours per quarter per full-time employee. The number of technicians increases as production scales throughout the year, leading to gradually rising quarterly labor expenses. In contrast, indirect personnel costs such as supervisors, logistics, administration, and marketing remain mostly constant across all quarters of year 1 since these support functions are required from the beginning. In year 2, labor hours per employee increases to 960 per half year, reflecting a more intensive production cycle. Direct personnel costs rise because of increased workforce, while indirect personnel costs also grow but remain relatively controlled. Next, we examine equipment cost. In year 1, we purchase essential tools, including injection molds, assembly fixtures, QC testing rigs, and handling carts, scheduled gradually to match production growth. Year 2 adds further equipment, maintaining control investment while supporting higher output. Material pricing is a key advantage. The complete filtration system costs only $1.05 per unit, covering plastic housing, activated carbon, iron resin, filter fabric, gasket, adhesive, and packaging. Whereas replacement cartridge cost about $0.54 each, encouraging affordable long-term use and repeat sales. Facility cost for year 1 is based on an 8,800 square foot setup, including rent, utilities, insurance, and other charges, all stable across quarters. In year 2, the facility grows to 15,200 square feet, increasing operating costs but enabling greater production. Our pricing strategy keeps the product affordable while profitable. Wholesale at $9.99, retail price is $13.99, and cartridges at $3.25, achieving a margin of around 36.44%. To launch successfully, total capital required is $643,200 allocated over phased stages, starting from tooling and prototype, pilot production, scaling, certification, and full deployment. Sales projection shows strong growth, reaching 1,300 thousand units and over $1.3 million revenue by the end of year 2. By the end of year 2, the cumulative contribution margin is about $655,400, which has fully recovered the initial fixed outlay of $643,200. The business therefore makes profit of $12,200 at the end of year 2. The cost revenue curve shows where earnings surpass expenses. This is the profit graph, shows how profit increases and more units are sold. And at the end, this is the cumulative profit graph, which confirms profitability around the end of second year. Thank you for listening.